Hi, I'm Parth, and I'll be going through formal logic today.
Hi, we'll first start with propositional logic. Propositional logic is the simplest way where we can express statements and reason over them with certain rules. So to start, we can start with propositional variables. Propositional variables are nothing but a reference to a state of an object, which essentially encapsulates the idea of them being true or false. Let's say there's a statement, it's raining today. Then we can assign it a propositional variable p, and when depending on whether p is true or false, it is either raining or not. So it is an object, it is a sentence whose truth value is encapsulated by this variable. And then this logical connection. Once we have this variable, we can use them with lots of symbols to enhance the our capabilities to reason over them. Some of them are like true and false. This is objectively true or objectively false. Then there's a negation symbol. Then there are conjunction, disjunction, implication, equivalence, exclusive or, which is just a negation of equivalence. Then there's punctuation symbols. These are essentially used to remove ambiguity. Make sure that your formula is precise and can only have one interpretation. Now, what are well-formed formulas? See, the reason we use punctuation to remove ambiguity, well-formed formula provides us a way to precisely define what a logical formula is. Yes. It leaves no room for a interpretation. So how do you form a well-formed formula? Essentially, well-formed formula, they have a core certain basics, the core of them, and then we inductively define them over them. Such as the base cases here are a truth value and a false value are a logical formula. And if P is a propositional variable as mentioned earlier, then P is also a well-formed formula. Now, after that, how do you define other formulas? You say that if such that let's say a formula F is part of a propositional formula, this negation is part of a proper well-formed formula too. Now you have let's say F and G which are themselves well-formed formula, then any binary operation applied over them in, encapsulated in this bracket is also a well-formed formula. See, the smallest subset condition ensures that the only thing constructible why these rules are admitted. The mandatory parentheses for binary operation are critical for ensuring unique and structural interpretation. Essentially, it means that your each and every formula is unique and has one meaning to itself and not others. This here. The parentheses are used for removal of ambiguity. Now, pass tree. What is the pass tree? Is essentially if you have a formula, say P or Q, let's say and A exclusive or B. Now, let's say this is a pass tree is just a way to di- a kind of way to deconstruct this formula. Let's say it's two part. One of this is you decipher it as P or Q, and then A, X or B. Then you can further divide them into P, Q, and then A or B. See here we are dividing the dividing a node or the parent of a tree into its children over a binary symbol, and each time we receive on either a propositional variable or a true or false, that is when we stop. AKA, it's the node. What this allows is it allows us to use the mathematical properties of tree to prove results. It makes proving results of propositional formula much easier. Such as this is just an example theorem of unit parsing. Every well-formed formula has exactly one parse tree. This property is fundamental as it guarantees the structure and consequence the meaning of any well-formed formula is unambiguous. To prove this, we use the property of the trees to make sure that this theorem is well proved. Now, subformula, the shorthand notation is used to essentially improve readability. It's an entirely human thing, human friendly. Try to make logic human friendly as possible. So you just assign to make sure that any when we remove parentheses to make sure there's no ambiguity, we assign you, priority order or hierarchy of logical operation. Where this operation this is the highest, then we have AND or XOR. and then we have these two which are the lowest priority. Now the most important part, semantics of propositional logic. What we have a, let's say we have a well-formed formula P or Q. Now this is a well-formed formula, but what does this mean? Assigning it to a statement or assigning a statement to a well-formed formula is what semantics mean. So let's say truth values and model. The set of truth value is just 0 or 1, where 1 represents true and 0 represents false. This is an arbitrary choice. That there are two states, truth and false. We just assign 1 to truth and 0 to false. It's convention. A model or truth assignment M is a function M which is essentially from variable to binary. Let's say in your scope you have this variable A1, A2, A3. Now each of them can be either assigned true or false, true or false, true or false. Any specific combination of this is essentially what M does is it states this variable and then maps it to any one of its possible outcome. Let's say it can be 1, 1, 1. All of them true, all of them false, or first true, both false. Any of the possible outcomes. Each of this mapping is a each of this mapping is essentially a model. This is let's say this is model M1, this is model M2. So the way we refer to it is that in under model M1, all A1, A2, A3 are true. Now let's see the satisfaction. A satisfaction relation, a model M satisfies a well-formed formula F. If under the assignment of model M, this assignment of model M, if F is true under the assignment of model M, then we say that M satisfies F. Now the way we determine it is similar. It's inductively. A model M always satisfies a truth because the truth it doesn't is irrelevant on any variables or assignment. For true is always true. There's no model which can generate true on a false. Now if model M satisfies P, that means that the assignment which gets under the model M is 1. Then if model M satisfies negation of F, that is equivalent to saying the model M does not satisfy F. So model M not satisfying F is nothing but model M satisfying its negation. Now we can say binary operator. Model M satisfies F1 and F2. F1 disjunction F2 if it satisfies both. It model M satisfies F1 or F2 if it satisfies either one of them, and M satisfies F1 implies F2 if and only if uh, either it does or either the model doesn't satisfy F1 or it satisfies F2. Now truth table. Truth table is essentially it just lists all the possible value of variable. Variables in propositional logic have either true or false. That's the only state they are allowed to be. There's no other way to interpret them. So let's say that k variable, it have 2 to k possible models for it or assignments for it. So the truth table just gives you the value of a well-formed formula f, the what it resolves to under all of these 2 to the power k models. This is just an example. Let's say we have P and Q, P or Q, and then not P and not Q. So if F is P or Q and not P and Q, not Q, then there's no assignment of P or Q under which F will return true. So this we can say is a way that model there's no model which satisfies F. This is for all models, aka F is not valid. Now we have these definitions: satisfiable, unsatisfiable, valid. Satisfiable means that there is at least one model under whose assignment the well-formed formula F is valid. Unsatisfiable is the same here. There is no assignment under which the well-formed formula will return false or return true. A valid, we say a formula F is valid if under any and all model M, it is true. Now logical consequence equivalence. Logical consequence, a set of formula sigma entails a formula f returns sigma f follows sigma if for every model M in which all formula in sigma are true, f is also true. Essentially, what is sigma is a set of well-formed formula, and f is a well-formed another formula such that if for any model where M satisfies all of the elements of sigma, then it also means that M satisfies F. If we have any of this formula under sigma, now if there's a model where each and every one of this is satisfied by M, where M satisfies all of this model, then it is guaranteed that M will also satisfy our consequent model. This means that if there's certain set of formulas which a certain model satisfies, then we can say that this formula is implied if M satisfies both. Consequence. To determine this is just an example of how the system works. Now we have logical equivalence. Two formulas F and G are logical equivalent if they have same truth value in every model. AKA, no matter what your variable assignment is, if the truth value of F and G is same, then we can say that they are logical equivalent. The best example is double negation. No matter what F is, if you negate F and then negate the negation of F, you will get the same value as you did in F. Now, equisatisfiability is F and G are equisatisfiable if and only if both are satisfied. Meaning that if F is satisfied, it is guaranteed that G is a satisfiable model. If G is a satisfiable model, then so is F. Now we have formal proof system for propositional logic. Essentially, till now, if we have something to check, let's say there's a well-formed formula F. If we are to check that whether it is the formula is true given from a set of other formulas, then what we have to do is we have to check for all model which satisfies each and one of these the preceding condition, and then we have to manually check whether they satisfies for F or not. We can infer, so to surpass this, we can essentially infer conclusion based on a well-defined rule system. So a formal proof system, it allows us to surpass this cumbersome method of manually checking for every model by essentially making sure that we can derive something from a set of assumptions. While semantics defines truth for a model, a proof system provides a syntactic method for establishing consequence using rules of inference. So here a statement, this means that F is derivable from a set of premises sigma. Sigma is assumptions, and we say that if these assumptions are true, then F is also true. Now we have various different types of proof system. The most important one we'll be dealing with is the natural deduction one. This system we focus here uses no axiom but a rich set of introduction and elimination rule for each connective. We'll just see here basic and derived proof rules. Essentially, there's some assumption monotonicity. We have ways of each operation. Let's say you want to say that sigma is a certain set of assumption from state that okay, from this assumption it follows that P implies Q. Then we have to introduce it. We can say this equivalent to if we assume P to be true, and from this assumption it implies Q. We can derive Q from this. Then we can say that it is similar to saying that if sigma is true, then P implies Q. These are just example. Now we have first order logic. What is first order logic? First order logic is just expanding the scope of propositional logic. In propositional logic, our variables were simply either were true or false. We were not able to reason over the scope of this variable. Let's say we have a set of numbers, and to represent that okay, at least one of them is even, or one of them is odd, or one of them is prime. There's no convenient way to do it in propositional logic. Now, first order logic is an expansion of propositional logic. If we take a first order logic system, then propositional logic will follow as a subset of this system. Now, the way we represent first order logic, there's a logical symbol which are same as propositional logic, and or negation implies this quantifier for all there exist, punctuation, and there's this equality sign which we'll learn later. There's non-logical systems such as the F, which is just a set of functions which is essentially takes a term and outputs a term. And now we have R, a set of predicate symbols. Essentially R is just a set of predicates which take in some value and return true or false. So now terms and atomic formula. Term is all the variable x are a term. Any constant symbol c is also a term. Now a function always returns a term. This inductively defines what terms are. Now atomic formulas are the most basic statement that can be true or false. If a predicate is symbol, then a predicate of any terms is atomic formula. If T1, T2 are terms, then T1 equals to T2 is an atom. This is either true or false. And obviously true and false themselves return true and false, so they are atoms too. Now we learned about well-formed formula as propositional logic. Now this is well-formed formula in first order logic. Here to make a proper well-formed formula, every atom is a formula. If F1, F2 are formula, then any combination with unary or binary operation is also a formula. This is the new one. If F is a formula and X is a variable, then for all X F and for there exists an F X for which F are also formulas too. Now free and bound variable is a very important concept. By definition, free variables, an occurrence of variable at X in a formula is bound if it falls within the scope of a quantifier. Now what it means is, let's say we have a formula, there exists an x which follows p of x. Now versus p of x. The main difference between this is the truth value of p of x is entirely dependent on what x is. Changing what x is on the assignment x, just the truth value of this formula too changes. But the truth value of this formula, there exists an x such that p of x, no matter what x you give here, the truth value of the statement is independent from the actual variable assignment. So you can say that p of x prime of x, there exists a number x such that it is prime of x. Now whether you take x as 1, x as 2 or x as 17, the truth value, there exists a prime number, is independent from whether we what value we take x as in a certain assignment. So semantics, there's S model. A non-empty set DM is called domain or universe of discourse. This contains all the non-logical symbols we use. Now for each function, essentially an S model M. S model M essentially means that we just have a certain functions. Model M takes the variables and assigns them values, and then S is just taking, let's say our function F and our predicates are, then it defines what our various functions are and what our predicates are. So the set of function and set of predicate is just a S, and then what M is assignment of variables to its values.